Hello, everyone, and welcome. Today, we're going to explore two fascinating and powerful models in the field of educational technology, EKT and GKT. Think of them as advanced tools that help us understand how students learn. Specifically, we'll look at how they trace a student's knowledge state by analyzing their interactions with exercises and the underlying structure of knowledge itself. By the end of this session, you'll have a clear picture of how these models work and why they matter for personalized learning. Let's get started. Here's the roadmap for our journey today. We'll start with a quick introduction to see how knowledge tracing has evolved. Then, we'll dive deep into three innovative models. First, EKT, which we'll call the teacher who looks at the exam paper. Next, GKT, or the knowledge subway map, which shows us how knowledge is connected. After that, we'll explore deep IRT, the self-calibrating ability ruler, which measures student ability in a smart way. Finally, we'll compare these models and discuss how you can integrate these powerful ideas into your own research. It's going to be an exciting exploration. Let's start with EKT. Imagine two teachers. The first teacher, let's call them standard KT teacher, only looks at the final score on a student's report card. They see a correct or incorrect mark and update their opinion of the student's ability based solely on that. Now, the second teacher, our EKT teacher, is different. They take the time to look at the actual exam paper. They see which specific questions the student got right and which ones they missed. If a student gets a tough question wrong, the EKT teacher understands that this might not mean the student is weak overall, just that they struggled with that specific topic. This deeper insight is the core idea of EKT. It's not just about the outcome, but about the journey and the specific details of the student's performance. So, how does EKT work under the hood? Let's break down its core components. First, we have exercise embedding. Think of this as translating each question into a unique digital fingerprint that captures its essence. Then we have knowledge components, KCs, which are the fundamental skills we want to teach, like understanding fractions or writing a thesis statement. The Q matrix acts like a bridge, connecting each exercise or question to the specific KCs it tests. The student state vector is the model's way of keeping track of a student's current skill level across all these KCs. It's like a dynamic skill profile. Finally, the prediction layer uses all this information to forecast how likely the student is to get the next question right. Together, these 5 parts work in harmony to create a detailed and accurate picture of a student's learning journey. Let's walk through a simple example to see the magic of EKT. Suppose a student tries to solve a math problem that requires 2 skills, algebra and geometry. In a traditional model, if the student gets this question wrong, the model might inaccurately lower the student's proficiency score for both algebra and geometry. It's a case of guilty by association, but EKT is smarter. It first checks which skills the question actually tests. Then, it updates the student's skill level only for those specific skills, and it does so in a nuanced way. If the mistake was clearly an algebraic error, it will adjust the algebra score more significantly than the geometry score. This is the key finding. EKT avoids the one mistake, all skills punished problem. It provides a much fairer and more precise update to the student's knowledge state. Now, let's move on to GKT, which stands for Graph-Based Knowledge Tracing. Let's use another analogy. Traditional knowledge tracing models treat each skill a student needs to learn as a separate, isolated drawer in a cabinet. Learning how to add doesn't affect your ability to multiply, according to this model. But we know that's not how learning works. Skills are connected. GKT changes this by thinking of knowledge as a subway map. Each station on the map is a specific skill, like addition or grammar. The lines connecting the stations represent the relationships between these skills, like how you need to learn addition before you can tackle multiplication. When a student learns or forgets a skill, a station, this creates a signal that propagates through the connected lines, affecting their understanding of related skills. This interconnected view gives us a much more realistic model of how knowledge truly develops. So, how does GKT calculate this propagation of knowledge? Let's break it down. The core idea is message passing. Imagine each skill or node on our subway map can talk to its neighboring skills. When a student practices a skill, that node sends a message to its neighbors saying, "Hey, I've just been updated." The graph convolution part is like a smart listener at each node. It takes all the incoming messages from its neighbors and combines them with its own current state. It's like updating your opinion on a topic after hearing feedback from all your friends who are experts in related areas. The calculation process is a cycle. First, every node gathers information from its neighbors, then it updates its own state based on that information. After one full cycle, the entire map of the student's knowledge is updated, showing the ripple effects of learning across connected skills. Next up is Deep IRT, which offers a fresh perspective on measuring student ability. Let's think about a ruler. A standard IRT ruler is a fixed measuring stick. It has a set scale, and it uses that same scale to measure every student's ability and every question's difficulty. But what if the ruler itself could be smarter? That's Deep IRT. It's a self-calibrating ruler. Instead of using a one-size-fits-all scale, it understands that a student's ability isn't a fixed number. It can change depending on the context, the time of day, or the topic. Similarly, a question's difficulty might feel different to different students. Deep IRT dynamically figures out both the student's current ability level and the question's actual difficulty in the moment, leading to a much more accurate and personalized assessment. Deep IRT cleverly combines the best of both worlds, the theoretical foundation of classic psychometrics, IRT, with the power of neural networks. Here's how it works. It takes the raw data of which student answered which question correctly or incorrectly. Then, its neural network acts like a sophisticated interpreter, trying to figure out two hidden things: the student's current ability level, theta, and the difficulty, beta, of each question. It's a bit like a detective trying to deduce two unknowns from a series of clues. Once it has these two values, it uses a standard formula to predict the likelihood of a correct answer. The model constantly refines its estimates of theta and beta to make its predictions as accurate as possible. The most exciting part is its high interpretability. Unlike some black box AI models, the numbers it produces for ability and difficulty have clear, real-world meanings that educators can understand and use. So, how do GKT and Deep IRT stack up against each other? They're both powerful, but they serve different purposes. GKT is like a city planner. It excels at showing the big picture, how different skills are connected, and how learning flows through this network. It's perfect for understanding the structure of a subject and identifying prerequisite skills. Deep IRT, on the other hand, is like a precision scale. It's not as concerned with the map of skills, but it's incredibly good at giving you a precise, up-to-the-minute measurement of a student's current ability level and the actual difficulty of a question. So, if you want to understand the how and why of learning pathways, GKT is your tool. If you need a highly accurate individual assessment of a student's performance, Deep IRT is the way to go. The real power comes when we combine these models. Let's say you're a researcher. How can you use GKT and Deep IRT? First, use GKT to map out the entire landscape of a subject, revealing which skills build upon others. Then, use Deep IRT to get a precise reading of where each student is on this map right now. Now you have a powerful system. You can guide students along the optimal learning path. You can even find their optimal challenge zone, OCZ. that sweet spot where exercises are challenging enough to promote growth, but not so hard that they cause frustration. And the future is even more exciting. By feeding in more data, like how long a student spent on a problem, how many times they tried, or even where they looked on the screen, we can create even more sophisticated models that understand the complete story of learning. Let's quickly recap what we've covered today. We started with EKT, the model that acts like a teacher who reviews the exam paper, focusing on the what. What specific questions were missed and why? Then we explored GKT, the subway map model, which focuses on the how different pieces of knowledge are connected and influence each other. Finally, we learned about Deep IRT, the smart ruler, which focuses on the how much, providing a precise, interpretable measure of a student's ability and a question's difficulty. Each model offers a unique and valuable lens through which we can understand and support the learning process. And that brings us to the end of the main presentation. I hope this deep dive into EKT, GKT, and Deep IRT has been insightful. Now, I'd love to hear from you. If you have any questions about the models, their applications, or how they might fit into your own work, please feel free to ask. Let's open the floor for a discussion. Thank you all so much for your time and attention today.